What do airplanes, laser beams, mountains and valleys, submarines, and roller coasters have to do with math? Well, those are all ways that I use to describe some of the qualities of a function and their graph. We'll see how mathematicians describe different qualities of graphs here in today's notes. Let's get going. Welcome back, guys. We are starting our next target, which really talks about the qualities and characteristics of graphs. So we're going to be looking a lot at visual properties here with these notes. Now I'm going to try to do something a little bit different, and we're not going to go problem by problem. We're probably going to skip through and talk about qualities for all the problems. I think it's helpful to see one characteristic or one trait across many different graphs. That way you get experience and expertise with that quality. But before we can do all the problems, we have to know the definitions. So let's go ahead and let's look at problem number 1. We have this graph. It's a pretty wavy, up and down, squiggly, curvy graph. And based on where it's going and what it's doing, we can talk about it in different ways. Similar to how you and I might talk about a person having different traits. Maybe they're tall or short, maybe they're muscular or thin. All of those things can describe people, and mathematicians can describe graphs in similar ways, just with new words. So the first idea is something that you're familiar with. It's called Xintercepts. If we're defining that, that's the point, or potentially points, there could be multiple, where the function crosses or touches the x-axis. Now, the y value for these places will always be 0. That means the height will be nothing. It never leaves up off the x-axis. And you have to remember with these, points are x, y. Very important. So if we're looking at this first problem, the x-intercepts, where it crosses that horizontal axis, would be at -2, 0, 0, 0, the origin, 1, 0, and then 3, 0. So in total, there are 4 different places where our graph crosses or is equal to the x-axis. We'll go ahead and we'll tie the next one with it. They're very related. That vocab term is y-intercept. These are just the points. Again, a point is x, y, where the function crosses the y-axis. Now, the x value for these particular points will always be 0. You're never moving left or right. You're just going to be going up and down. So 0, something is how these will look. If you're looking at our graph, it is actually crossing the y-axis right at the origin. So 0, 0 is a special point. It is the only point that is both a y-intercept and an x-intercept. If it had been shifted up a little bit, we would have a positive y-intercept, and if it had been shifted down, we would have a negative y-intercept. So let's go ahead and let's look at x and y-intercepts across all of our different graphs. If we look at problem number 2, this graph is a little bit different, and we're going to have different x and y-intercepts. So the x-intercepts here, there are 3 of them, occur at -4, 0, 1, 0, and 4, 0. The y-intercepts, if you're looking on that vertical axis, and y-intercepts up there a little bit at 0, 4. Now you have to make sure you're getting the order correct, because in this problem we had 0, 4, and then we had 4, 0. Which of those is the x-intercept and which of those is the y-intercept? You have to be able to tell those apart. If we move on to 3 and talk about intercepts, this graph doesn't really have a nice coordinate plane to see heights and things like that, and that's going to be tricky later on. But thank goodness it doesn't really impact the x and y intercepts, because those happen at the axis, which we're given. Now we have 4 different x-intercepts. They happen at -4, 0, the origin, 0, 0, 2, 0, and then 6, 0. If we look at the y-intercept, it is 0, 0 because it's the origin. That's the only spot that can go in both of these traits. Moving right along, if you flip the page at number 4, number 4 and number 5 actually are graphs that have some similar qualities. And so we put them next to each other to kind of challenge you and make you think a little bit more critically. The x-intercepts for number 4 happen at -3, 0, 0, 0, and then 3, 0. A little bit of symmetry or patterns there. The y-intercept, since it goes through the origin, is the origin, 0, 0. Now for number 5, if you are really looking there, it has the exact same x and y intercepts. It goes through -3, 0, 0, 0, and 3, 0. The y-intercept is the origin again. Now, if they have the same x and y intercepts, does that mean they're the same graph? Absolutely not. You can clearly see here that they are two different shapes, two different functions. So different people, different functions might share traits in common and have the exact same answers, but be very different in other ways. With those problems, you should pretty much be an expert on x and y intercepts. It's a basic idea that you've covered through previous math classes, and so hopefully it was nothing new, just brushing off some of the dust. If we go back to the first page, where all the definitions are, we're going to learn a new idea, a new quality. And this idea, it's called relative maximums or relative minimums. Now you should already know what maximum and minimum mean. Maximum just means most, minimum means like least, smallest. So you have this idea of biggest and smallest, but relative here really makes a difference on what we are looking for. If we're defining these are the points where a graph changes direction from increasing to decreasing, or potentially from decreasing to increasing. This is where my first analogy comes in handy. It's kind of like going hiking. And when you hike, you can climb up to the top of a mountain, where in that region, you are at the highest point that you can go. Or potentially hiking down and being in the bottom of a valley, where the water would collect. You can't go any lower because water always goes to the lowest point. Now, relative here means that it doesn't have to be the absolute maximum or the absolute minimum. Sometimes graphs won't have an absolute maximum or minimum. That means you can never reach the top of the graph or the bottom. They just go on forever in either of those directions. So when we say relative, we just mean in that small region. Okay, if you were to draw a little bubble, are you at the highest point in that bubble? Are you at a mountaintop? If you were to draw a bubble, are you in the lowest point, a valley? And so what I encourage students to do is to go hiking along the graph. Start on the left, hike your way through and see if you come across any valleys or mountains. And here's how I like students to write their maximums and minimums. Tell me which one it is. So first we have a maximum, and this graph is a little bit harder because there's not really a vertical scale, so we'll estimate. But as we're going from left to right, I think we reach a maximum, a mountaintop, right around 1/2, so 0.5. And if we go up, we're at about 1.5. So you list these as points, x comma y. So 0.5 comma 1.5. Now that's not the only mountaintop. This is a problem with a mountain range, multiple mountaintops. And so actually the taller mountain is over a little bit further. It's at 2 comma 4. And again, those are both estimates in terms of height. If I really wanted this problem to be a little bit better, I should probably put a scale on the y-axis. That would help. So what about minimums or valleys? As you were hiking, did we come across any of those? Well, hopefully you see that there are actually two. The first one happens over at -1, -3. So water would collect down in that bottom point. There is one more. It's a tiny one, but it still is technically a valley in that relative region, and that is at 1 comma 0. So 2 maximums, 2 minimums. You do not have to have the same number of both, but you need to be looking out for both, and you need to be labeling which ones are which. So let's try this with the rest of the problems in the notes. Problem number 2, if we're hiking along this graph, and start from left to right, just like how you read a sentence or write your name, we have 1 maximum. That's the first thing we come across. We get to a mountaintop, and that's at the point -2 comma 5. So you would write max, -2 comma 5. Now there's an interesting point next to this maximum, next to this mountaintop. If you hike just a little bit further over, right at 0 comma 4, is that a maximum? Now think about what maximum means. It's the highest point in that region. So if you drew a circle, is that the absolute highest you could be? And if you look a little bit to the left of the y-axis, there are some points that are a little bit higher. So you could potentially get a better view. You could get more altitude if you just climbed a little bit further over. And so even though this flattens out, it is not a maximum. It's not the highest point in a region. It's just a point where we kind of come to a smooth, level surface. It's a bit like a cliff or a ledge, not a mountaintop. So we can't count that point in the maximums. If we keep hiking, we eventually get down to the bottom of a valley, and that occurs at 3 comma -2. Afterwards, we keep going to the right, and we travel up and up and up and up, and we never reach the top of a mountain again. Just like how when we started, we were coming from the bottom, and there was no valley down there. It continues in both directions. The arrows on a function do not count as maximums and minimums, and that's because they don't stop. Problem number 3 is like the Himalayas. We got a lot of action going on here. This is definitely a whole mountain range. And so for the maximums, the tops of these mountains, you can see that we're going to have 4 of them. The first happens at -4, 0, and then at 0, 0. 2, 0 is another mountaintop, and those are pretty close together in terms of heights. And then 6, 0. Now you'll notice the tops of the mountains are actually the same as the x-intercepts. And that's because this graph never seems to go past the x-axis. It's trapped below, which is actually a different quality we'll talk about later. For the minimums, the valleys, we're going to have to make estimates because, again, this graph does not have a scale on the y-axis. We should probably improve that for the future. So our minimums. If I'm going over and estimating, it's about 3 to the left, and it looks like it's going to be down around 6 if we put some tick marks as our scale. So -3, 6. We have another one, not quite to 1, so it's about 3/4 of the way over, about 0.75, and down maybe 1 unit. And then the last valley where it would collect water, this is a deep valley, happens over at 4, and then about down 6. The first valley and the last valley are at about the same depth. For the problems that we give you, they will have a scale, so you won't have to be estimating. But just for the notes, it's good to get some practice with some unusual graphs. And overall, estimating is a good skill to have. So what about with the last 2 problems? Maximums and minimums, mountaintops and valleys. If you're hiking along number 4, you can see that you're hiking up, and then eventually you start to go back down, which means you came across a mountaintop. That's a maximum at -2, 2. All right, that's the point where it is the highest in that region. As we travel down, we reach a level spot. That's not a maximum, it's not a minimum, it wouldn't collect water there, and it's not the top of a mountain, so we cannot count that point at the origin. It's kind of like a ridge or a cliff or a plateau. Going past that, we have a minimum or a valley over at 2, -2. If you kept hiking further to the right, you're never going to reach a mountaintop again. It just goes forever. And so just 1 maximum, 1 minimum in this case. The last problem for maximums, if we're looking, there's only 1 spot where we have a mountaintop, and that's right at 0, 0. Now that mountaintop is actually sandwiched in between 2 valleys, and so the minimums here are at -2, -2, and then 2, -2. So you have valleys and a mountain in between. You cannot count the arrows on the left and the right side of the function because they go forever. They never come back down, so it's not a mountaintop. Hopefully these ideas make a little bit more sense after hearing the analogy of going hiking, and that's something you're going to need to remember whenever I ask you for relative maximums or relative minimums. Let's go back to the front. So far these notes probably haven't been that bad. You're familiar with x and y intercepts, and maximums and minimums are just this idea of hiking. But as we work through the table, things get a little trickier, and this is the first point where people trip up usually. Now, we're going to be doing increasing intervals and decreasing intervals at the same time. They're related, and you should know what the words increasing and decreasing mean. So increasing means getting larger, getting bigger, or potentially getting higher. Decreasing means getting smaller or getting lower. So we have this idea of size or height. Now, if we're defining an increasing interval, it's very important to understand what an interval is. An interval, to a mathematician, is a range of x values. And so this is kind of like how long, what duration is it doing this thing? And so for an increasing interval, that is just the span of x values where a function's y values or heights get larger. And it's very important that you're moving from left to right. For the second idea, decreasing intervals, it's just the span of x values where a function's height or their y values are getting smaller as you move from left to right. And my analogy for this, to make it a little bit clearer in students' heads, is that an increasing interval is similar to when a roller coaster is traveling up a hill. You're increasing in height. And you need to know how long is that happening. Same thing for decreasing. This would be like going down a roller coaster. Okay, going down a hill. How long is that hill? That's what we're interested in knowing here. And so the notation has to reflect that we are looking at how long, the span of x values. So for this problem up top, we're going to try to highlight so you can see this a little bit better. First, intervals, since they are x values, have to have the letter x in front. That way, whoever is reading this knows that you are now talking about x's the entire time. Because what comes next looks like a point, but it's not. If we are traveling along this roller coaster, you have to get on all the way at the left. Now going over there, the graph itself starts up above the x-axis, and so we're starting all the way up here. We had to climb the stairs to get to the top of the roller coaster where you get on. So we're getting on the roller coaster, and the first thing that happens as soon as we start is we go down a hill. Now that idea should say decreasing in your mind. So we're going to be in this second box where the decreasing intervals are. Now this is hard. How long are we decreasing? At what point do we reach the bottom of the hill and we start to swoop back up and climb up? Well, that happens, if you're looking left and right, at -1. That's where we reach the bottom and we start going back up. And so we stop decreasing and then we go to increasing. So at that point in time, at -1, we switch. Now, the hardest part about this is knowing, when did you start going down the hill? How early were you decreasing? And it turns out if you had extended the graph a little bit, our function would be even higher. And so you could have climbed on earlier in the roller coaster, and the first thing you would have done is you still would have decreased. And it doesn't matter how far left you expand this. So what we're saying is that you can get on as early as you want. You can keep going left, and if you get on the roller coaster, you will decrease right away, no matter where you start from. And so what we have to say is that we are decreasing from all the way to the left until -1 in terms of time. Now, all the way to the left as a number to mathematicians would be -infinity. It goes forever and ever and ever in the left direction. So it doesn't matter where we get on, we will always be going down the roller coaster until we get to -1 as our point in time. Now we said at -1 it switches, so we go up the hill, and so you got to imagine yourself increasing up that hill. And so from -1 in time all the way to about 0.5 in time. Think about this almost like a video timeline. If you're cutting and snipping, like what's the duration that you would be going down the hill versus going up the hill? And so from -1 to 0.5 for x values, we are increasing, and so we'll write that up in the increasing interval box. Now once we get to the top of that hill and we're looking down, we're going to be decreasing, going down a hill. Now it's not a very big hill, so it's from 0.5 in time all the way to 1 in time. So it's just a little, and then we're done. But the decreasing interval here happens over a little short unit, from 0.5 to 1, and so we'll write that down below. If you're following the roller coaster, we've gone down and up a hill and then down a short hill. Now at that point in time, at 1, we're going to go back up. And we aren't going up a big hill, okay? It's not a very long hill in terms of duration. It happens from 1 as an x value to 2 as an x value. So from 1 to 2, you are increasing and going back up a hill. We get to the top of the hill, we're looking down, and we can see, this is going to be a ride. From 2, that point in time, for how long? What's happening for the rest of this roller coaster? Well, you would be decreasing and going down a hill. So imagine, from 2, forever. You're going down a roller coaster, so you might be going down this roller coaster for the rest of your life. You're going to die and be like rattling around as bones on this roller coaster. You know, what a morbid thought that you'll die here. And so we're decreasing from 2 in time to infinity in time, forever. So you have to understand that the axis goes in both directions forever. It never stops. So negative infinity is where it's coming from, and positive infinity is the idea of what it's going towards. Now all of these look like points. 1, 2, 0.5, 1. That's why we need to be really careful with the notation, and that's why you have to have the x in front, because this says x values from here to here. It's not 2 comma infinity. It's not that point. That point doesn't exist. Infinity is not a number. It's this idea of forever. Hopefully those highlighted regions help clear this up. You're talking about time duration. You're talking about x values where that happens. And as you get more practice, you'll get a little bit better at this. You'll get faster. But starting off, this is a quality that takes patience and really carefully looking at what's going on. Let's try the next couple of questions. With question number 2, if we're going to get on the roller coaster here right away, it is down on the lower left-hand side. Now, the first thing that this roller coaster does when you get in and you put your seatbelt on and everything is that you're going up a hill. And so we're going to be in that increasing interval box. Now, if you haven't already done it, I would put an X in both of those to show that you're talking about X values, or how long a duration you're doing one of these things. And so from all the way to the left, no matter where you get on, you're going to increase right away. You're going up the hill. And as we go up the hill, we continue and we continue until we get to the top. Now that happens at an x value of -2. So from no matter where you get on, all the way until -2 in time, you are increasing. You're going up in height. So from -infinity to -2, that is the interval, the first interval where you're increasing. Now after that point, you go, ah! And you're going down kind of a hill where it levels out. But at that point, we don't go back up again. It's just we get like a breather for a split second before the real drop happens. Okay, so from -2 in time, we're decreasing, decreasing, decreasing until we get to x value, a time of 3. So hopefully you're seeing that this is a horizontal recording. From -2 until 3, we are decreasing, and so that'll go in our decreasing interval. After that point, we're going to go back up, and if you're seeing where the roller coaster is going, how long are you going back up? Forever should be your answer. So you are going to live the rest of your life trapped on this math roller coaster, going up, and eventually you're going to start to run out of oxygen. It's going to get real hard to breathe, and that roller coaster is going into outer space, and so there you go. That's happy to think about. But how do we record that idea? Well, when did we start going up the roller coaster again? Happened at the x value of 3. How long were we going up the roller coaster? Forever. So from 3 to infinity is how we would record that. Now, one thing that you can do to kind of check your work is that all of these intervals should connect like links on a chain. You're either increasing or you're decreasing. And so from -infinity to -2, -2 will hook up to the bottom, -2 to 3, and then that 3 from the bottom hooks up to the top again, 3 to infinity. And so you go from -infinity to positive infinity. It's just, are you going up or are you going down? So that's one way that you can check and make sure that you're doing things correctly. Make sure they all fit. Now the third problem is a toughie, all right? Because this is a roller coaster that you would probably end up puking on, it's just up and down all over the place. We're going to have to fit a lot of intervals in here. And so the first thing, if you go all the way to the left, where are we getting on? Down in the bottom left. And so look at what happens right away. We are going up the roller coaster. And so from -infinity all the way until what point in time are we increasing? Well, that happens actually at the x-intercept at -4. So we're going up until we reach -4 in time. I keep moving my hands like this because this is how we should be thinking. So in the increasing interval box, we're going to say from -infinity to -4, we were going up. Now at -4, we actually transitioned to going down a big hill. It's pretty steep. So we would say from -4 all the way until about -3. That's where the valley happens for its x value. And so maximums and minimums are actually important here because they tell you the x values where you change direction. So -4 to -3 is in the decreasing interval. You went down a hill. Didn't last very long. It lasted about a second. Now at -3 we change. We go back up a hill. And so we're going up from -3 in time until about 0 in time. That's where the top of the hill is. We go down a short hill from 0 until about 0.75. And so that'll be in the decreasing spot. It's just a small, woo, baby hill. And then we start to go back up a baby hill at that point. So from 0.75 until what x value? Hopefully you're saying 2. So from 3/4 until 2 in time, you're going up a hill or increasing. From 2, you start to go back down a hill, and this is a longer hill. It takes from 2 seconds, or 2 as an x value, until 4 seconds, 4 as an x value. So 2, 4 is a decreasing interval. We are not done yet. This roller coaster has one more trick up its sleeve. It is going to go up another hill from 4 at time until 6 at time. You're going back up the roller coaster, and by this point, if you haven't lost your lunch, you're about ready to, because what's the last thing this roller coaster is going to do? You get to the top of the hill and you look down, because this thing is going to decrease forever. So maybe it like goes into the earth and then out through China and then the other direction of the world, and you're just falling for the rest of your life. From 6 to infinity, you are decreasing on this graph. If you can get a problem like that, then you definitely understand and you have expertise in increasing and decreasing. But it's the idea of riding this roller coaster when you're going up versus when you are going down that's going to help you do this correctly. Remember that you're only looking at the x values, so it's like a timeline on a video. How long are you doing either of those actions? We'll go ahead and finish up the last 2 questions, and if you ever need a break, feel free to pause the video. If I'm going too fast, you can pause it. Hopefully I'm not going too slow, but I really want to explain it so that you understand the concepts. So for number 4, if we get on this roller coaster, we're getting on in the bottom left. We're going up right away, so we're increasing. From negative infinity, forever to the left, we're going to be increasing until what point in time? And if you answered -2, you're spot on. So in the increasing interval box, we're going to put the x first off, letting me know it's x values we're talking about, negative infinity, -2. Now at that point, we actually go down. Don't worry about the part where it levels out, because it only levels out for a moment, but we're still going down after that. It's not like we're changing directions. So from -2 in time all the way to +2 in time. So that's a 4-second drop. After 2 in time, we're going back, and this roller coaster finishes going up a hill for the rest of its life. So it's increasing from 2 until infinity. And so we have the links in the chain hooking up there, negative infinity to -2, -2 to 2, and then 2 to infinity. There is no position in there where nothing exists or the roller coaster does something weird, so it's kind of a continuous action and a continuous quality. The last problem for increasing and decreasing intervals, again, think roller coaster. Getting on here, we're getting up above, and the first thing that you're going to do on this roller coaster is you're dropping down a hill. They just let you go. So from negative infinity all the way to what point in time? -2, hopefully is what you said. So from negative infinity to -2, I would be decreasing, so that will go in the decreasing intervals. Then at -2, we go up a hill for a little bit. So that's about 2 seconds worth of hill. So from -2 until 0, that'll be in the increasing interval. Then we switch, we go back down a hill, and so from 0 to 2 seconds, then we're going down a hill. Now a lot of people will want to say -2 because they're looking at the height. I don't care about the height of the hill. I care about how long of a time we are increasing or decreasing. These are x values, so you should never look at the y values. So the x value there is 2. Now at that point, you switch directions and you're going to be increasing for the rest of your life, going up the roller coaster, you'll die there. And so from 2 to infinity, forever and ever, you'll be an old man on this roller coaster, and everybody behind you will be old people, and it'll be terrible. Although some of you might prefer dying on a roller coaster right now to watching this video or being in class, which I kind of understand. Hopefully after those questions you have a little bit more confidence in being able to describe intervals, specifically here, increasing and decreasing intervals. The next quality that we do is going to be a little bit easier. So we had some hard work there, we're going to take a breather, and then we're going to do another hard one after that. So let's go back to the front. This next idea is called end behavior. And if you think about what that says, or what it sounds like, it's observing the actions that go on each end of the function. So the definition here would be a description of how the function's y values behave as the x values become very, very small, going towards negative infinity, or very, very large, going towards positive infinity. Now for my regular classes, I do this with a different expectation than an honors level. For kids who are in regular, I typically have them look what's happening as we're going further to the left and tell me what direction the function happens to be going. For the graph above, if we're looking to the left, as the x values get smaller and smaller going towards negative infinity, you can clearly see that the graph is increasing. The y values are getting larger. And so I would have my regular students just put an up arrow. Now as the x values get larger, going towards positive infinity, the y values here go smaller. They're going towards negative infinity. And so I'd have them put a down arrow. And so up on the left, down on the right is typically what I just have kids do for a regular level class. But for honors, I'm expecting a little bit more out of them. And we need some symbol notation that's going to be valuable when you get to calculus later on. Also being able to hear the words and the terminology is important. And so this is what I would say. As the x values approach negative infinity, that means as we're going left, the y values approach positive infinity. You think about the y values that we're seeing, maybe it's like 5 and 6 and 7 and 8, maybe it's 100 and then 1,000 and then 1,000,000. And so the y values are getting larger, and that's the idea of approaching infinity. Essentially the y values go up. Now on the other side, as x approaches positive infinity, as we get further to the right, is what that's saying, the y values decrease. They get lower and smaller and smaller. So the y values go towards negative infinity. The arrows in these problems just means approaching or going towards, and so you need to know what directions those are saying. X approaching negative infinity means going left, x approaching positive infinity means going right, y approaching positive infinity means going up, and y approaching negative infinity means going down. So that's the expectation for an honors levels class. Let's take that idea and apply it to the second question. The end behavior for this graph, as x goes towards negative infinity, the y values are decreasing. They're also going towards negative infinity. For regular, just a down arrow. But as we go to the right, as x values approach positive infinity, the y values here are also approaching positive infinity, so it's going up. For my regular class, that would be an up arrow, and for my honors classes, you would use the symbol notation with the idea of approaching those extremes. For the third question, this one's going to be a little different. As you can see on the left, as the x values go closer to negative infinity, the y values also go closer to negative infinity. It's headed down. So for regular, that would be a down arrow. On the right-hand side, as the x values get larger and as they're approaching positive infinity, the y values are decreasing. They're going down. So both sides of this function are decreasing in y values as the x values reach their extremes. For regular, it would be down on the left and down on the right. And for honors, you would have the symbol notation with the x's and the arrows and which extreme it would be going towards. For problem number 4, if we're following the same pattern, on the left-hand side, as the x's approach negative infinity, so they get more extreme, the y values are approaching negative infinity. They are also getting more extreme in the negative direction. So for regular, that's a down arrow. As we go further to the right, as the x values approach positive infinity, the y values are approaching positive infinity. That would be an up arrow for my regular class. Falls on the left, and it rises on the right-hand side. These trends are important later on when we talk about symmetry and things being odd or even functions. The very last problem, problem number 5, as the function approaches negative infinity for its x values, so we're going further left, the y values are going up. They're approaching positive infinity. So for regular, that's an up arrow. On the right-hand side, for regular, it's also an up arrow. But for an honors level class, you would say as x approaches positive infinity, as x gets bigger, the y values approach positive infinity as well. The y values get bigger. So all of these are just asking where the graph goes when the x's get extreme. Really, really small or really, really big. I'm going to go ahead and stop the video here. I don't want you to have too much all in one spot. Plus, this is kind of a nice breaking point between the first half of the table and the second half. I would encourage you guys to go through your homework problems and try the things that you learned in this video. You can always go back and reference some of the problems, and look through your notes. And if you have a question, feel free to contact me. Thanks for watching, guys. Keep up the great work. We're really proud of you, and we'll see you in the next video. Take care. To get to the top of this roller coaster, to get to the top